have run our fuzzer through it and found just about any bug that was previously published. However, the good thing about it was by switching to a new version of MadWiFi, we also found a previously undocumented vulnerability. And how easy it is to find this vulnerability using our framework. I'm just going to start the second. Oops. Resuming and the snapshot again. Yeah, it's an old machine. Okay, so we're inside a Kubuntu version, Kubuntu Linux, fairly recent kernel, and I've written a script for scanning. So this script does nothing else than activate our wireless network, and then, so I can really hardly, but it says IW list Atheris 0 scan, so it's just constantly scanning. And like I said before, we're simulating an Atheris device, so I can use LSPCI, and I can see down here that we have a network connection, a network card Atheris communication AR5212, just like I said before. So if I start my scanning now, I can see again, well, there are frames coming out to search for wireless networks, but this time I'm invoking my fuzzer, and I can tell my fuzzer what do I want to fuzz. I can tell him, well, I can either fuzz beacon frames, I can fuzz probe responses, and so on. I can tell it how do I want to fuzz it. I can say, for instance, I want to fuzz probe responses. I can tell it how do I want to fuzz the packets. Do I want just plain overflowing, or do I want to inject string format vulnerabilities? Just use overflows for now. And I can tell it, like I said before, I can tell it which packet do I want to fuzz. So I can wait for a certain event. I can simply use regular time interval, but I can also wait for a probe response, probe request to come in. And I can also tell it how often do I want to inject a packet. And since I know that the vulnerability is in information element 48, information element 50, I'm just going to start with number 48 and just invoke the fuzzer. You can see there's scanning going back there, and I see, okay, we fuzzed information element number 48, nothing happened. I inject beacon, so right now I'm waiting for a probe request to come in. And as soon as I get one, I fuzz my information element number 50, and you can see in the background, well, kernel panic, and it's even telling me where the problem is. So you see how easy it is to do stateful fuzzing, and also you can see that my fuzzer didn't continue fuzzing because it knows, okay, something went wrong. So with that, we can see, whoops, that was wrong. That was wrong. So we can see that we found a vulnerability in the last MadWiFi implementation. It was a frame that we send in about extended supported rates, and it totally crashes Linux systems. There's no remote code execution possible, but it's really easy to send out denial of service pack. So as soon as you will receive one, your system totally crashes. And together with SecondSalt and our Secure System Lab, we have published the vulnerability, and it's been fixed in the latest release of MadWiFi. Okay, so now to continue how we might use this vulnerability, I'm just going to hand out over to Sylvester, who's going to talk a little bit about kernel mode exploits.
Okay, I hope this works. So we listened to Jeff's keynote this morning, and we thought, how could we make our presentation a little bit more like a Darth Vader presentation? So we thought, well, we could, put in more and more content. So now I'm going to talk about kernel mode exploits. You just saw the kernel panic, and before we started fuzzing, of course, we asked ourselves, what kind of vulnerabilities could we find in kernel space, and if we found them, could we exploit them, and how could they be exploited? And also, or especially since we're fuzzing wireless devices, could we exploit them from a remote machine? And also, we asked ourselves, how generic could these exploits be? Could we, just come up with an exploit and put it into Metasploit, for example, so that if our fuzzer finds a vulnerability, we would be able to, adapt a few parameters and have a working exploit. So that would be really nice. So what we did, we started, reading lots of FRAC papers on kernel mode exploits, and we focused on Linux because we like Linux, and we also had initially only wanted to fuzz the MadWiFi driver. And the first thing that we found that I'm introducing here is a very simple, or very simple in theory. We included it because it has a few important concepts, and that's the so-called null pointer or user space pointer dereference vulnerability. And that's basically you have a pointer in kernel space, or a stray pointer in kernel space that points into user space. So if that pointer is dereferenced, then something unpredictable is going to happen. But now if you have a local control over the process in context, or over a user space process, you could simply mmap the area that the stray pointer is pointing at, and you could create all kinds of interesting exploit scenarios from there. So if you have a direct, or what's called a direct dereference, if it happens in the context of instruction execution, that would be a very trivial case to exploit. But there are also more interesting scenarios. For example, if you have here in the first line a call to kmalloc. Now, if that call to kmalloc fails for some reason, if there's not enough memory, or if you are in control of the size variable in some way and you can just make it insanely large number, and the kmalloc fails and is not checked, you might have a null pointer in the variable foo. And now, if sometime later something is written to that, or to a structure that is expected to be where foo points to. Now, foo is a null pointer, so it points to address 0. But address 0 is, of course, in the user space. And we just tried this out a couple days ago in the lab. It's quite funny. You can just, on Linux, map the 0 page in a user space process. And so you could just mimic the structure that's expected to be there. And of course, if you have control over, in this case, the data pointer, you could let it point anywhere you want it, and you would have a controlled write. And of course, there are many exploitable scenarios that can derive from this. So the next class of vulnerabilities that we looked at, or the problem with this class, of course, is that you need a local process. And for us, if we think about fuzz or exploiting wireless devices, we don't have that. So we looked at something else, heap overflows. We had this talk yesterday about heap overflows. In the kernel, you have the kernel memory allocator, which is normally the slab allocator. And you can set up so-called look-aside caches with memory objects that all have the same size. And when Linux starts, it actually creates pools of such caches with very small objects. And if you make a call to kmalloc, for example, it will simply pick one of these objects for you. So what is a slab overflow? A slab overflow is simply if you write beyond the boundary of one such object and into the adjacent object. So it's something like this. And again, you could try to exploit the metadata, but also the data, as we heard yesterday, that is in the next slab. But for this to work, you need to know, what kind of memory object is there that you're writing into, and then you could maybe exploit by overwriting a function pointer in that memory object. Okay, I just started and already get the red card. Again, that's something. These exploits work by forcing the kernel to create certain objects that can be exploited. But again, you need a local process to do this. And so we looked at Stack Overflows. Now, Stack Overflow's the kernel stack is different from the user space stack. It's only 8K or maybe even 4K. And you have, it starts at the top and grows towards the bottom. And at the bottom, we have the thread info structure, which points at the process descriptor. And I mean, in theory, the Stack Overflow exploit works the same for kernel stacks as for user space stacks. You place your shellcode in a buffer, and you want to override the return address. So, but that's the first problem. How do I know where my buffer is? So you can use the chump ESP trick. That if you know a chump ESP instruction somewhere in the kernel memory, you could, point to that, and after the return instruction, the stack pointer will be placed to the memory object right above your chump ESP address. And so there, because that's basically in your overflow, you could point back to the beginning of your buffer. You wouldn't even need the knobs in this case. But that's already the start of the guessing game. You need to know where is the chump ESP in your kernel. And also you need to know where's the return address that you're overwriting, because we had it up here, but it could be down there also. And what if I don't know it? You could do a similar trick, and that is insert the address of return instructions in the kernel space. Then you would just basically after the first return, the ESP would point or the return would pop off one value from the stack, and you would return again and again and again until you hit your chump back to the beginning of the buffer. So that way you could, if you knew the chump ESP address, you could hijack control flow in the kernel. But that's only the start. We're here either dealing with a system call, so we're in the context of a process, but we might also be in interrupt context. In fact, if we talk about wireless devices, we're probably in an interrupt context, because a packet will arrive and the interrupt will be triggered. Probably it will set up a tasklet, so to defer execution, and we will run later in a soft IRQ context. But again, we will not have a user mode process in our context. And the thing is that kernel mode exploits sound very cool, but at the same time, you'd like to get back to user space, because you can use all kinds of libraries, and it's harder to really mess up there. So you would like to come back, but if you're in a interrupt context, you don't even have a user space process, or you don't know which process, and it could be a critical process that you cannot really hijack. So what you'd like to do is you want to set up your exploit or place it somewhere else where it's safe, and install a hook for later on. And then you would have a user space process later on triggering your hook that would then execute your second payload or copy it to the user space process and execute it there. So if you take this concept, you would like to have exploits that look something like this. You have the kernel mode exploit wrapped around a normal user space exploit that you can send to the target, and ultimately it will execute your user mode exploit with root privileges. And that's exactly the way Metasploit tries to handle Windows kernel mode exploits. And it does this by dividing the exploit into these sections. We have migration, staging, recovery, and the stage. And this is basically what we saw on the previous slide. Migration, you need migration if you, for example, are in an interrupt context. The stager basically copies your payload to a safe location for later on. And recovery is something that's very important too, because if you're a stager, you know, you have set everything up for later, but